Hello, everybody. My name is Rodrigo Veras. I'm professor from Universidade Federal do Piauí, and I'm here today to present our paper P-FideNet, Plasmodium Falciparum Identification Neural Network. This research was done in cooperation with Daniel Cruz, Maíla, Claro, Luiz Vogado, Helano, Portela, Nayara, Moura, and Daniel Luz. Some of the research are from Instituto Federal do Piauí and others from Universidade Federal do Piauí, both in Brazil. So this is the outline of my presentation. I'll start with an introduction to present you the malaria disease. I'll talk about the related works. And in materials and methods, I will present you the image dataset used, the evaluation metrics, and the proposed methods. After that, I will show the results, make a discussion of these results, and make a conclusion and future works. So, during the last decade, specialists from most diverse fields, such as biology, computer science, and the others, started to contribute to make more complex and precise image analysis methods. The main purpose of these systems is diagnose disease, like, for example, malaria. Malaria is an infectious disease transmitted by a parasite mosquitoes. The transmission includes infections of red blood cells by protists of some genera. Among the most common and deadly types of malaria are the variants Plasmodium falciparum and Plasmodium vivax, where the first is the most harmful type. According to the last report from the World Health Organization, published in 2019, is estimated to more than 200 million of confirmed malaria cases in 18 countries, with more than 4,000 of these will occur death. The early diagnosis of malaria is the essential method for its control, since it enables to perform the treatment before the progression of the transmission. However, malaria symptoms are often indistinguishable from symptoms caused by disease such as viral hepatitis, a dengue, and many others. So the diagnosis is really a challenge. Uh, the purpose of this paper is to automate the identification of cells infected by Plasmodium falciparum. And we choose to do this with a CNN that we call P-FideNet. But why we use CNNs? So we did a search in the state-of-the-art methods, and we can see in this table that the most important papers in the area use it as solution convolution neural networks. Some of them customized CNNs, in other words, they build your own CNNs, but others papers use the transfer learning technique to fine-tuning some well-known CNNs like VG19, HESNET, and Inception. We can see that the accuracy of these methods could be considered good. So we decide to follow in this line of use CNNs in the malaria diagnosis or malaria detection, but we try to build a CNN with a low number of parameters. To this, we use an image dataset and developed by the NIH malaria dataset. This image dataset is pre-processed and labeled, and the images were achieved with the use of a microscope and the camera. The data set consists with more than 27,000 images from blood cells and is well balanced with the same numbers of health samples and infected by Plasmodium Falciparum samples. To evaluate the methodology, we use four metrics: accuracy, recall, precision, and F1 score. So this is the architecture of P-FideNet. This is the P-FideNet architecture. We can see that the input layer has the length of 3, 50, and 50. After that, the image is submitted to a dropout layer followed by a convolutional layers. We have 3 main convolutional layers with length of 32, 64, and 128. After each of these convolutional layers, we applied a max pooling layer and a dropout layer and a flatten. Finally, we have 2 fully connected layers, and between them there is another dropout layer. This model has a similar feature as a sequential architectures present in the related works, and was based on VGG16 and VGG19. So to test, train, test, and validate our approach, we rearranged the image data set in 3 folds, composed of 18% for training, and 10% for testing, and 10% for validation. The experiments were performed using Python, in Python language, using some libraries like Keras, Matplotlib, and TensorFlow. And we also use Google Colab to run the tests. This table in the last line shows the results cited for our methods. We compare the results obtained with our proposed architecture with some other architectures to define the best approach. For this, we choose CNN architectures that presented excellent results in the ImageNet contest. We picked the architectures with a relative low number of parameters compared to the other sequential CNN. So we applied a fine-tuning within these architectures here, and besides this, our P-FideNet has achieved better results than the others. We can see in the last column or the last row that our P-FideNet has much less parameters than the others CNNs in the state of the art. So the proposed method achieved a better performance than other CNNs, besides having a smaller amount of parameters, make the model much less computationally expensive. According to the results, we can note that the number of parameters is 39 lower than HisNet 15, for example. And to better understand the results, we plot the charts with accuracy and loss. According to the charts, we notice that the validation and training curve similarity for accuracy and loss. This result proves that the model is stable and robust. It is also observed that the gap between training and validation loss, as well as accuracy, reduced significantly over the epochs, indicating a first model convergence. And here we can see some results of our methods, where the first result means the ground truth, and the second, the prediction of our methods. Here we have samples of where our method was okay. So we compare the results of our proposed method and those obtained by the studying the state of the art. These comparisons is very effective, so because the methods listed here use the same image dataset and using the same metrics. We can see that our results are competitive with the other methods proposed in the state of the art. But remember that we have a less number of parameters than all of these ones. So we conclude that in this paper, we presented a new CNN architecture, the P-FideNet, to provide an important improvement, in the classification of malaria and an image of red blood cells. For future works, we intend to analyze our neural network to understand weak points, expand the existing data set by applying data augmentation techniques, and another methodology to be applied will be the migration of the current model to a device-oriented architectures, such as the mobile nets, as the low number of parameters of our architectures allow us. So I appreciate your attention, and I finish my presentation here. See you.